All right, sorry for the delay on this video. I was going to do it last night, but I had no voice. And so this is our video for Monday, the dominant view from classmates expressed in the quizzes on Wednesday was to do the full chapter 14 for Monday and the very short chapter 15 for Wednesday. So that's what we're doing. All right, so first question we're going to explore is this one. How can we explain Earth history? And this entire chapter is basically about giving you a foundation of geology and then going through and point by point trying to assess how does an interventionist view or short age geology differ from a conventional geology view. So just big picture here, how can we explain Earth history? The interventionist geology or short age geology suggests that a great deal of the fossil record, a great deal of the geological column was laid down during about a year during a global catastrophic flood. Now, while this presents some interesting issues in that we have never seen a global catastrophic flood, we have seen, large scale flooding events, but to try to figure out what a global flood would do is very challenging. Just the scale of that is incredibly difficult. And so it does present some interesting difficulties assessing the a short age geology, but it is certainly testable if we are very careful with the predictions that we make and very careful with how we interpret data. Not only is a short age geology view testable, but in time, if what the Bible teaches about Earth history is true, which we have good reason to believe that it is, in time the data that accumulate should favor a short age geology or an interventionist geology more than conventional geology. Okay, and so conventional geology is basically heavily influenced by James Hutton and Charles Lyell's views of uniformitarian geology. And that really has four applications talked about in the text. One is uniformity of law. And the idea here is that the physical laws that govern the universe and the natural world have not changed. And so that's one aspect of this uniformitarianism. The next one is uniformity of law. Oh, sorry, that's the current one. Uniformity of geological processes. And so what this is basically there are no unique events other than modern processes. So even if you're going to appeal to some catastrophe to explain a geological feature, it needs to be done in terms of events that we have seen, geological processes that we know. And so even this one, the uniformity of law is no issue for an interventionist position. Uniformity of geological processes, this one is a little bit more difficult, but we do have evidence to suggest that there were events in the geological past that were indeed different than current processes. The next one is uniformity of rates of processes, and that's that geological processes have always been slow and gradual. There have not been any geological or catastrophic geological events. We now know this is false because studying taphonomy and understanding how organisms are fossilized, virtually everybody appeals to catastrophe as they explain certain parts of the geological column. The other one is uniformity of conditions. And so this idea is that conditions on Earth have always been the same, cycling endlessly. But again, we have reason to believe, just looking at the fossil record of the organisms that appear early versus late, that this is not true, that the conditions on Earth have changed. All right. So going to the next one, how do rocks form? And so this is very much just a foundational understanding of geology. And so we have different types of rocks. Igneous rocks form when molten magma cools. And so there are a number of examples of igneous rock. Here's a granite. We also have basalt, volcanic lava. And so the continental plates are heavily granitic, uh, and the oceanic plates that underline the ocean are heavily basaltic. And both of these form as molten magma cools to contribute to these plates. And we see that it's an active process. This is not a static process, but we are continuously forming more and more igneous rocks, especially as they contribute to growing oceanic or continental plates in one location as they're being subducted and melted back into magma in another place. Igneous rocks very rarely contain fossils because this process of of starting as a liquid magma at incredibly high heat would typically destroy anything inside anything in the organism. Now, there are exceptions to this. If you can surround an organism with volcanic ash or even lava that has cooled to the point in which it's almost hardening, that you can actually get some fossils in igneous rock. Sedimentary rock basically forms in a four-step process. Older rocks erode. They then are so they erode into smaller particles. Water or wind or glaciers, which we'll talk about a little bit later, transport this material to a basin where then it is deposited. And then, so that's step three, deposited out of that medium, whether water, wind, or glacier, and then is cemented into sedimentary rock. All right, sedimentary rock is the primary rock in which you find fossils, and the rate of deposition plays a large role in how you can even fossilize something inside of it. So sedimentary rocks, we tend to group them based on the size of the grains or particles. So we've got shales and siltstones that have very small grains. We've got sandstones that have larger sand-sized grains. We have conglomerates that are a mix of fine particles like sand and mud, and larger rounded pebbles. And then we have breccia, which is similar to a conglomerate, but the larger pebbles are not rounded. They are angular. And so that's an important factor there, and we'll talk about this a little bit later, is suggestive that they were not transported in water. And then the final type of sedimentary rock we have is limestone, usually calcium carbonate, but you have whatever this material is precipitates out of water, out of ocean water, or rivers, streams, or lakes. And many of these limestones are calcium carbonate from the shells of organisms, corals, mollusks, foraminiferans, and yeah. And then our last type of rock is metamorphic rock. Metamorphic rock happens when rocks that are already formed are subjected to heat or pressure, maybe by being buried under a lot of other rock, or they are chemically changed and it transforms them into a different type of rock. We call these metamorphic rock. These, like igneous rock, rarely have fossils because this process of metamorphosis or metamorphism, sorry, metamorphosis is biological forms. Metamorphism typically destroys what fossils may be in that sedimentary or very rarely igneous rock. Weathering is another important process. When you're talking about rock formation, weathering is a process of altering rocks and is the first part of the sedimentary process. Groundwater and weak acids seep through rocks, breaking them down, and then the minerals get changed. The minerals in the rock get changed into clay or dissolved ions or quartz and other sand-sized grains, and then these can be carried to other places where they influence water chemistry, and then they can actually form sandstone formations somewhere else. But here you can see the influence of weathering on a rock formation where we have lost some of that, and then all of that material has then been deposited somewhere else. All right. Oh, so how long does it all take? How long does it take for this process of sediment accumulation? How long does it take for this process of erosion? In an interventionist or short age geology, we're given thousands of years rather than hundreds of millions or even billions of years. And so these processes have to be much faster. And so we have some issues there. Radiometric dating suggests that these rocks are old. The amount of biological organisms, and we've talked about this before, the fact that when you look through the fossil record, organisms seem to get more sophisticated and more complex. So we have some issues with this, but there are evidences that these processes of especially erosion, but even sediment accumulation, can happen much more quickly than typically assumed. And so here's an image of a canyon behind Dr. Brand's house, a canyon carved out during a few heavy storms in a matter of months. Whereas if you do the calculation, you would calculate that it would take 30,000 to 49,000 years to form this, and instead this was formed in a single rainy season. Probably, Dr. Brand says, in a matter of 2 to 3 weeks, and then so you can actually form this incredibly quickly. Whereas conventional geology, we've seen this before, uniformity of law, water's flowing downhill, that's not an issue. Uniformity of geological processes, again, that's not an issue. It's water carving this, which we would assume regardless of, or we would interpret this as water formed regardless of whether we had seen it happen or not. Uniformity of rates of processes, that's a huge issue. So small amounts of water require enormous amounts of time to deposit sediment and to erode away other rock. Large amounts of water can do this very, very quickly. And so that's a big issue. Conventional geology would suggest that this, again, was 30 to 40, it took 30 to 49,000 years to build this canyon. But in reality, it took just a few weeks, maybe a couple of months. And they talk about this in the book. Basically, they built a road up there, didn't drain it properly, and it shifted the drainage pattern of water. And so when you had a rainy season, the water ran into a new area and carved out this canyon pretty quickly. And so in the text on page 315, there is a diagram that basically then takes this and applies it to the entire fossil record. And in the conventional geology theory, because we assume uniformity of rates of processes and uniformity of conditions, we've observed a certain amount of rock formation, and we extrapolate that back in time to estimate the rate of erosion and sedimentation throughout time. Whereas in a short age geology, we have a massive amount of water, and so we would suggest, because we know with large amounts of water, large amounts of sedimentation and erosion can happen in short periods of time, and in a global cataclysmic flood, you're obviously going to have a large amount of water, and we would suggest that much of the earth could actually be shaped in a fairly short amount of time. All right. So how are sediments deposited? And so this really, regardless of your view on origins or your particular commitment to a philosophical view, you have to recognize certain things about how sediments get deposited. So in this figure here on the left, we have basically an illustration of the size of rock that can be carried by water, and that the size is dependent upon the flow rate of water. Fast moving water can carry really large rocks. And so here you have this up higher where you have really fast moving water, several creeks or several streams coming together to form a fast moving river. Here you get the river opens up a little bit, slows down, and so you don't get the massive boulders, but you get still pretty large size materials. And then finally here, this is where the river really opens up, flow rate really slows down. It no longer has the energy necessary to carry large rocks, but instead carries just sand-sized particles and then drops them as it flows. And then finally, even beyond that, when the water pools, things like clays and silts that would typically stay suspended in the water can fall out as well. Another thing that we need to talk about here is that when water carries rocks, it tends to round it as the energy of the water carries the rocks and bombards them against other rocks, bombards them against the solid substrate underneath the river. It tends to round out those rocks, and that's going to be an important thing to keep in mind as you start thinking about how do we explain these particular environments, which on Monday, that's what we're going to focus in. There's a portion of this chapter that just goes through, I think, 3 or 4 different environments and explains what's going on there, how were they deposited, and could we explain them from short age or interventionist geology. Over here on the right, we have a graph that illustrates what the velocity and depth of water and the particle size, what impact that has on the features of your rock. Basically, I'm going to sum this up this way, and this is something that's important to keep in mind. The faster your water moves, the more irregular the ripples are in the rock. Okay, and so fast-moving water leaves ripples in the sediment as they're hardened. And so we can look at that and determine whether these sediments were deposited in a river or were deposited in a lake, were deposited in a slow-moving river or in a fast-moving river by looking at the ripples in the rock left by the wave activity. And obviously that's also going to be impacted by the particle size, and you can see that as well here. The rule here is the larger your pieces of material, the potentially more irregular your ripples are as well. But particle size is a little bit easier to see even in the rock, whereas wave activity you have to infer from how the rock was actually put together. All right, and then the next portion of the chapter actually gets into those 3 specific environments and talks about how were they deposited, and we'll focus in on that on Monday, and also if we have some time, we'll do some additional work as well. So this question should actually read, how was most of the geological record deposited? Although you could do the fossil record as well. So studying the fossil record and seeing the number of organisms that appear there and the type of sediments suggest that most of the Paleozoic and Mesozoic were deposited underwater. And so from a conventional geology perspective, you would explain this by having these, inland seaways that are depositing materials. In an interventionist or short-age geology, you would explain this as a global flood that essentially covered the entire Earth's surface. And so it would make sense why most of that record, which is typically interpreted as part of the flood deposits, you would interpret that as happening during this global flood when the entire Earth's surface was covered in water. All right, so how do we accumulate so much sediment? something that you have to keep in mind regardless of your view of origins and how you process this. Conventional geology, again, is going to be heavily influenced by uniformitarianism, and so the rate of sediment deposition is going to be the same as what's currently happening now, and is going to be very rarely influenced by massive catastrophic events unless you have some kind of a mass burial event. But something that has to happen, and this is a figure that came out of the text, is as sediment accumulates, this basin actually needs to sink to make room for additional layers of sediment deposition. And so in order for accumulating more layers, the whole idea here is water always flows downhill. And so if you're going to create a basin for sediment to accumulate, it has to be a lower elevation than the surrounding area. So if you're going to continue to deposit sediment and to accumulate sediment, you have to actually have this basin sink. And in a short age geology or an interventionist geology, this has to happen much, much faster than what geologists interpret or think that they actually happen. And this is an interesting issue. This has to happen regardless, again, of your view of what shapes the bulk of the Earth history. But again, it's something that has to happen really quickly in short age geology. Next thing is how do we form mountains? So mountains can form by a number of different processes. And so this first one is folding. And so in folding, you basically have compressional forces that will uplift and then fold the sediments into waves. This is not heavily influenced, indirectly influenced by the molten magma underneath. A lot of this is because of these solid plates pressing in on each other. Fault blocks form when a section or blocks of the Earth crust moves up or down along a fault line. Then you can have erosional remnants where you had basically a continuous elevation of material and parts of it are eroded away, leaving a remnant. You could obviously form mountains through volcanic activity as magma pushes up through the crust and then cools. These you're going to expect to be made primarily of igneous rock. And then these last two are both intrusions of magma. In a laccolith, you have the magma pushing up between sedimentary layers and never breaks through the surface. In a batholith, you basically have this magma that pushes everything above it. You're not pushing some magma up in between part of these sedimentary layers and then trapping in between. In a batholith, everything is being pushed up. Every layer of that rock up above is being pushed up by intrusion from magma. Now, what we find is that mountains form by a combination of these processes. It's very rare, in fact, to have mountains formed by just one of these processes. Probably the two most common in terms of the mountains that we have in North America are going to be a combination of folding and then erosion, leaving a remnant. And the text actually talks about this, that there's evidence to suggest with the amount of sediment we have accumulated in valleys outside of the Rocky Mountains, that the Rocky Mountains were at one point closer to 30,000 feet tall in many areas, and a lot of that is eroded away. All right. So how can we form mountains? The process of mountain formation, and we actually see these in activity, are the same regardless of your philosophical commitment, although again in short age geology this has to happen very rapidly. So the nice thing is we can use these processes to figure out the order of events. And so in here, here's a figure from the text, and it gives these order of events. Number one, we already had this granitic layer present. This is a continental plate made again primarily of granitic rock. Step two is you formed several sedimentary layers here. And then in step three, you had this uplifting event. You had this folding. We can tell that these sedimentary layers were deposited before that because they are uplifted in the same way that this granitic layer is uplifted. Step four is we have additional sedimentary layers deposited, and you see these are all horizontal, suggesting that they happened after the uplifting event because they are not uplifted like these sedimentary layers are. And then steps 5 and 6, you have basically what we call a cut, where we have basically penetration of the layers by magma. 5 and 6, we can tell that these layers were already present when that happened because they cut through those sedimentary layers. And then in 7, we have more sediment deposited that was not penetrated by this magma infusion. Therefore, it must have happened after 5 and 6. And then finally, 8 is a shift of these along a fault. And we can tell that that happened last because it actually shifts all of the layers along that fault line. And so we can use these processes of mountain formation and use these processes to figure out an order of events, which is really important if we find fossils in these layers to know when did these processes actually happen. So the next one we need to talk about is glaciation. So glaciation leaves particular remnants. A couple of things that you tend to find in glaciation events is you tend to find U-shaped valleys versus V-shaped valleys. U-shaped valleys are carved out by the movement of glaciers downward from a mountain, and this is because it scours the side, whereas a river tends to just pull material from the bottom of the material from the bottom, and then as it gets deeper and deeper, water hasn't had as much time to act, and so the valley is narrower. The other one, you have what are called cirque basins. Basically, as the glacier moves along this rock, it cracks the rock, and then these areas can freeze because of the presence of this glacier, which cracks the rock even more. And then as the glacier moves, it pulls these pieces of rock off that fall into the glacier, and leaving amphitheater shaped basins called cirques. And so another sign of glaciation is along where the glaciers are moving, they are scouring this rock, basically polishing them, and as they drag debris against that underlying rock. And then the last one are moraines, basically small little hills formed by glacial till. And the thing here, glacial till, the materials in that are not well sorted like they are in water. So high velocity water brings large materials, lower velocity water, medium size, and then really low velocity water, small size. And so you tend to get particle sorting in water deposited in environments. In glacial deposited environments, you don't get sorting. And so this glacial till, these hills are just a accumulation of a number of different particle sizes, ranging from pebbles to really large clast, all basically packed together. I think I said that was the last one, but the last one is actually erratic boulders, where you just have a massive rock that doesn't match the surrounding rock type present, and the only way to really explain that is that you had a glacier penetrate into that area, and then leave behind a remnant. And so the question is, how much of this has actually happened, and and how long did that take? Now we have present places in Greenland and in Antarctica where we have a huge areas of glaciation that aren't just glaciers forming on a mountain and then sliding down the mountain, but are covering entire, sometimes almost entire continents covered by these glaciers. And as the glaciers expand, they're going to carve out material, and then as they retreat, they're going to deposit that material behind. And so there are evidences throughout North America and Europe that suggests that we had glaciers that penetrated pretty far down into the continents. And you can see evidence of that with having glacial till and glacial remains and erratic boulders and highly polished underlying rock, the bedrock. And so it suggests that in the Earth's history that the glaciers were more extensive than they are now, suggesting particular ice ages. And so the question is, how do we account for this, really, regardless of what your view of origins is? So in order to get an ice age, what you need is unusually cool summers. And so the textbook talks about the year there was no summer. It talks about evidence of Pleistocene glacial evidence. Where you had this massive ice age, and you had glaciers that penetrated into South Dakota and New England and Michigan, even Washington State. And so what's interesting here is, one, we have historical records from the Swiss Alps were in AD 60. They weren't actually frozen over, and AD 600, sorry, and people could actually pass through them. From 1450 to 1850, there was a little ice age, and documenting very cold weather where the River Thames froze over, which it doesn't any longer. And then you have 1816, they're referred to as the year without a summer, where New England had 6 inches of snow in June and reported snow in every single month of the year. And so what's interesting is you had a series of volcanic eruptions in 1812, 1814, and 1850, 1815, suggesting that enough material may have been put into the atmosphere to keep the summer cool enough that you could actually have that snow accumulating and sticking around all year long. Now, what's interesting is we have evidence of a lot of volcanic activity during the Cenozoic. And so some would suggest that may have caused the Pleistocene ice age, this massive ice age. What's interesting, though, is that only works if the Cenozoic is not millions of years, 64 million years, but is actually a short period of time, and could explain from a short age geology what precipitated the massive Pleistocene ice age. All right, so how much glaciation happened? There's evidence that a lot of it happened, and very extensive evidence to suggest that we need to come up with some way in which we can explain how you can form an ice age. The next question, and we're getting towards the end, is there any place on Earth where you can find the entire geologic column? And the answer to that is no. I mean, there's no place on Earth where you can find Precambrian, go into Cambrian, all the way through the Paleozoic, Mesozoic, and into the Cenozoic. But if you work north of and south of the Grand Canyon, you can basically get all of it. The Grand Canyon at the very bottom has Precambrian rocks. a number of a large portion of the Grand Canyon contains Cambrian deposits. The Grand Canyon only has Paleozoic sediments, and there are some sections that are missing from the Grand Canyon. For instance, in the Grand Canyon, there's no Ordovician or Devonian deposits. You actually have to go further north to find those. But then you do get the Carboniferous broken down into Mississippian and Pennsylvanian, and the Permian. Now, if you go north of the Grand Canyon, you can find Triassic deposits in the main Copy Formation and the Chinle Formation. In the Vermilion Cliffs here, we can find Triassic deposits containing dinosaurs. And if you go a little bit further north, you can find, like in Zion National Park, it should be up here, you can find Jurassic deposits and Cretaceous containing a number of dinosaur fossils. And then if you go even further north, we get into Utah. You get Cenozoic deposits, including recent deposits. And so you don't get all of the geological record in the Grand Canyon, but moving a few hundred miles north and south of it, you can get a great deal of the geologic record. And so conventional geology would suggest that it's 540 million years or so from the Cambrian to the present time. And in short age or interventionist geology, we're dealing with thousands of years. And so there's a question is, do we have reason to believe that deposition could happen that quickly? And again, in a global flood, while we have no record of what a global flood is like other than what scripture tells us, and if you think most of the world was deposited during that, but a global cataclysmic flood could explain this. How are organisms fossilized? This is something we have to keep in mind. We've talked about it before. Here's the taphonomy of a panda bear. Panda bear falls down a cliff. Panda bear dies. Here you have panda bears decomposing, and then you have some kind of a event that separates the bones out, and so here we're left with just a disarticulated, disorganized skeleton washed down somewhere. And so we have to keep in mind that this process of decomposition and disarticulation can happen pretty rapidly. And the only way to fossilize this is to bury it very rapidly. And so, knowing that and knowing the sheer number of organisms that we have in the fossil record, again, suggests catastrophes, and that's why most, or not most, or maybe most, but many, interpretations of particular areas in the geologic column are interpreted as local catastrophes. Although if we have a global catastrophe, then obviously this has the capability of depositing enormous amounts of sediment in a short period of time, bearing a number of different organisms.